Hi, hello, welcome. This is Discrete Mathematics, and today we are covering section 1.2, Propositions. The study of propositional calculus is the study of logic involving statements that are either true or false and their logical operators, the types of things we can do with them. This section is our introduction to logic. We're going to continue on talking about logic throughout the rest of this chapter. The statements which are either true or false are called propositions. Propositions. Here we have our first example. We want to determine whether each of these statements is a proposition or not. Statement number one, the sky is blue. So that statement is either true or false. Most of us would consider that that's a true statement. And so that is a proposition. 2 plus 2 is 5. This is not a true statement, but it is a statement that is true or false, and it's false. St. Francis is a Catholic university. That is also a proposition, also true. Please do your homework. This doesn't really have a true or false value. This is a command, a very nice command. And so this is not a proposition because it does not have a value that is true or false. X minus 3 is 11. This depends. Its truth value depends on the value of x. So it's true sometimes and it's false sometimes. So this is not a proposition because it depends on whatever x is. Happy New Year. This is a statement, but it doesn't really have a truth value associated with it. So it is not a proposition. What time is it? That is a question, and questions are not propositions. So propositions are statements that are either true or false. When we talk about propositions, we often use letters and symbols. Letters to represent the propositions and symbols to represent the logical operators. Propositions, often we use P for proposition, and then we a lot of times have more than one proposition. So we use Q, R, sometimes S. So we're just following in alphabetical order here. Our logical operators, there are 3 of those. We'll talk about them more. But and, or, and not. Those are our logical operators that we're going to talk about today. So here are 2 propositions. 1, the sky is blue. And 2, it is raining. So P is the sky is blue and Q is it is raining. So we can use some logical connectives to talk about these 2 statements together. The first one is called and it's with this symbol right here. This symbol, the way I remember it, it kind of looks like the N in the word and. And in set notation, so for sets, we had an intersection, which looked like A and B. And that kind of looks like this symbol as well. This is called the conjunction, and we use the word and. So P and Q, if I was going back to the P and Q I have up here, it'll be the sky is blue and it is raining. Which you wouldn't think that those 2 would happen together. So maybe this logical connective would be false because we're not going to have both of those together. But a lot of the times today and in our next class, when we talk about propositions, we're not really mediating the value of the proposition itself. We're talking about a set, an argument of different propositions all strung together. We'll talk more about that next time. Next up is or, logical connective or. And in sets, that is similar to the union. A union B, A or B, is called the disjunction. It's joined with or. P or Q, the sky is blue or it is raining. If you do any programming, the symbol and in languages like Java, JavaScript, C++, I think even Rust, will use like a double ampersand to represent an and when you're doing logical statements in that language. Python, which is a newer programming language and tries to be more user-friendly, actually uses the word and. So that's kind of nice. And or, oftentimes they use the double vertical bar, except of course Python uses the word or. So if you're programming, you might see double ands and these double vertical bars to represent these logical connectives. Okay, here we are at example 2. Statement P is 3 minus 11 equals 8. Statement Q is ice is cold. So let's evaluate the truth value of P. Is 3 minus 11 8? 3 minus 11 is negative 8. So this this statement is false. Ice is cold. That statement is true. Now I want to consider P and Q, and then I also want to consider P or Q. Are they true or false? P and Q. Let's see. P is false. Q is true. So false and true is going to be false. Let's look at P or Q. P or Q is false or true, and that is going to be true. So how do we decide whether something is true or false? Let's look at our truth tables. This first truth table we have here is for and. And in this over here, we have every combo of true and false for P and Q. So we have true, 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 false, false, true, and false, false. So when we're looking at the connective and, we're looking for, if you have one of the results false, then our whole thing is false. The only way to get a true statement with an and is if everything is true. And that's what we see up here. So if I have one is false, that means that the whole thing is false. Next up, we have or, and this is the inclusive or, which is the one we typically use for math, and that means one or the other or both. P or Q or both is true. That implies that the whole thing is true. Result is true. So here we see, here's a true, so that's true. Here's a true, 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 true. The only way to get false is if both of these are false, then you get a false. This is called the inclusive or. This is the one that we'll use as a default when we're talking about math and logic and things. There's also one called the exclusive or, and it uses this symbol, X or. This is usually what we mean when we say an English statement, like you can have orange juice or apple juice. That doesn't usually mean both. It usually means you have to pick one. You can't have both. And here we see that represented here. If both of them are true, then that's false. You can't have both. You have to pick one or the other. So one is true and one is false. And then that's how you get the statement to be true. So P or Q is true, but not both. We won't see this one as much. The default case, if it's not specified, is this one, the inclusive or. Another thing to note when we're talking about truth tables, this is true for all truth tables, when we are looking at filling out P and Q. So when you fill out a truth table, you're filling out this whole side. You want every combination of P and Q. So if you only have two statements, P and Q, then you'll have 4 rows in your truth table. If you have P and Q and R, then each of these has 2 choices, true, false, true, false, true, false. So you'll actually have 8 rows in your truth table. If you have 4, if you had P, Q, R, and S, this is going to be 2 to the 4th power, which will be 16 rows. So you can see as you get more and more statements, your truth tables are going to become bigger and bigger. So we're not going to do truth tables beyond 8 rows. That's already a lot of rows. And we're going to look at some other rules as well next time about how to deal with multiple statements. Okay, here we go. Example 3. P is a student can have a salad with dinner, and Q is a student can have soup with dinner. And I want to write out in words each of these 3 items: P and Q, P or Q, and P exclusive or Q. P and Q, a student can have a salad and soup with dinner. Student can have both. You're probably very happy about that. Let's say you're really hungry. Or, this is our inclusive or. A student can have a salad, a soup, or both with dinner. last one, exclusive or. A student, can have a salad or soup, and then I'm going to put in parentheses, but not both with dinner. Just to be clear that this is the exclusive or. I could have done something, I could have rewritten this one in a similar way. A student can have a salad or soup or both with dinner. Okay, next up is the negation symbol, and that is this guy. And if you are into programming, this is often represented by an exclamation point. Not equal to, for example, would be exclamation point and then equal to, not equal to. So we often will throw the word not into a sentence in order to represent this negation. So if P is the car is red, not P is the car is not red. So notice when I do this, I've broken up my proposition and I've added the word not like in the middle of it. Another thing that I can do, sometimes it's difficult to decide where to put that not, especially if you're stringing multiple propositions together. So one thing that you can do, an alternative way to express not, is by saying it is not the case that, and then you write your statement without any modifications. The car is red. So then I haven't actually modified the proposition itself. I haven't had to tuck a word in there somewhere. I've just added this at the beginning. It is not the case that. This doesn't quite sound as natural, but sometimes when you're unsure of where to stick the not, you can get by with the negation by adding this thing on the front. It is not the case that. Next one, P, my smartphone has at least 32 gigabytes of memory. Not P would be my smartphone has or doesn't have at least 32 gigabytes of memory, but the opposite of at least 32 gigabytes of memory would be less than 32 gigabytes of memory. So here's another example where I've actually changed some of the words to make it more contextualize what not means in this case. I could also do my alternative with this one. It is not the case that my smartphone has at least 32 gigabytes of memory, but I'm going another step and making it a little bit more contextualized. What does not, the opposite of at least 32 gigabytes? It's less than 32 gigabytes. Moving along to evaluating logical propositions. There is an order to evaluating these things. Much like when you did algebra, there was an order to algebra operations. I don't know if you've ever heard of PEMDAS or please excuse my dear Aunt Sally, parentheses, exponents, multiplication, division, addition, subtraction, order of operations. Here we have an order of operations for logical operators as well. The first thing you do is parentheses. That's kind of similar. And then you do not, and then or. So let's do some practice here with A, B, C, and D. We are going to evaluate these ones. And let's see, P is true, Q is false, and R is true. So we want to evaluate these propositions. So I have not P or Q and R. So if I look up here, I don't have any parentheses. So the first thing that I want to do is this one, Q or R. I think before I do anything else, I'm going to write the value of these. So not true or false and true. So what I want to evaluate first is this with the and. Oh, and this, I guess. I want to do both of these. So not true is going to be false or false and true. So in order for an and to be true, both of them have to be true. So this one is false. False or false is false. So that is my result, false. Let's take a look at B. Not, and then in parentheses, P or Q. I'm going to rewrite this. Not, and in parentheses, P is true and Q is false. And I am going to do what's in the parentheses first. true and false, which is false. So not false is true. Keep going with part C. First, I'm going to write true and false or not true. So the first thing I'm going to do is this right here, the not true, true and false or false. Now I'm going to do the parentheses, false or false is false, true or false, which is, or sorry, true and false, which is false. Last one, not the quantity P and Q, or the quantity R and not Q. So let's see, this is going to be not. I think I'm going to go ahead and do this P and Q. P is true, Q is false, so true and false is false. Or R, which is true, and Q, not Q, which is true. So let's see, not false is true, or true and true, which is true. I don't need these parentheses anymore. So true or true is true. Okay, so this is one way we can look at things. Here is a truth table with 3 propositions, P, Q, and R, and you can see I've got every combination of P, Q, and R. True, 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 false, true, false, true, true, false, false, etc. And I see that there's 8 of them. I start out, there's 4 trues and 4 falses here, and then I have true, true, false, false, true, true, false, false, and then true, false, true, false, true, false, true, false. So this is every combination of true and false. And I look at the statement that I'm evaluating, this over here, that is the same as this one. It's the same as A. And so I've already done one of these. I've done the true, false, true one. That's this one. So I've actually already done this one in part A, and my result here was false. So now I'm going to look at doing this statement with all the rest of these, and I'll fill out a truth table for every variation of P, Q, and R. So let's see, I'm going to have false or Q and R is Q. So now I'm looking over here for my values for Q and R. Q and R is going to be true, so false or true is true. Now let's see, I've got false or true and false, which is false. So this one's false. I already did this one in part A. Now I've got false or false and false, which is false. False or false is false. True or true and true, which is true. True or true is true. True or, and you know what, I'm noticing all of these. These are all going to be true or. And true or, it doesn't really matter what's over here. This or only requires that I have one of the sides be true. It doesn't really matter what the other side is. So these are all going to be true. I don't even need to really calculate the rest of it. A true or false is true. A true or true is true. So it doesn't really matter what these question marks are. I can save myself a little time and not fill out the rest of the, not figure out the Q and R for the rest of these, because the result is going to be true either way. So that is example 4. I've extended 4A here into this truth table for every possible combination of P, Q, and R. This was an example of one where I had just the statements like with symbols. Next up, I have each proposition with words, and I want to represent that proposition using symbols. Here, P is there is a hurricane, and Q is it is raining. Represent this proposition symbolically. There is no hurricane. I'm looking at hurricanes, so that's proposition P. There is no hurricane is going to be not P. In B, there is a hurricane, but it is not raining. So there is a hurricane. This word but, another way that I can write that is and. So there is a hurricane, but, or and, it is not raining, not Q. Either, So here's your cue that we're going to do or. There is a hurricane, or it is raining, or both. This is the one that is our default case, the or both. So this is the inclusive or. So there is a hurricane, or it is raining. P or Q. Here we practiced taking our propositions and writing them with symbols. And that is the end of section 1.2. We will see everybody next time.